Oh, let's go into a second type of curve sketching problem. This one's going to go over a rational function, meaning a function where you've got variables in the denominator. Oh yeah. So we're going to do this the same way that we did the first video, which is state out all your pre-calculus information and all your calculus information. So let's start with the pre-calc information. First and foremost, I always factor what I'm working with. So I factor out a GCF in the numerator, and I get 3 times x squared minus 1 all over x minus 3 times x plus 3. It's actually slightly more I could do to factor this thing. All right, the numerator can go into x minus 1, x plus 1. So not so bad. Now notice that nothing divides out here, so we don't have any holes. Right? To go way back to our chapter 1 work, we don't have any discontinuities that are removable. Okay, so let's keep rocking and rolling from here. So now, from this, I can figure out a host of information. Number one, let's look for any x-intercepts. Okay, well, if I've got an x-intercept, remember that happens when y is equal to 0. So that will happen when my numerator is 0, but my denominator is not. Well, the numerator is equal to 0 when x minus 1 is equal to 0, or x plus 1 is equal to 0, right? I mean, take a look at it. 1 minus 1 would give you 0. So there's x equals 1. And negative 1 plus 1 would give you 0. So those are my two x-intercepts. As points, they would be 1, 0 and negative 1, 0. Now don't wait to plot them. Go ahead and plot them right away. So I've got 1, 0, boom, negative 1, 0. It feels like you're kind of graphing as you go. It feels like you're accomplishing things. It's nice. Let's look for a y-intercept. So now as far as a y-intercept goes, remember that's going to happen on the x-axis. That occurs where x equals to 0. So we literally can plug in 0 for x in any of these expressions. They're all equivalent. So I like plugging it into here. I think it's easier. So if I plug in 0, I get 3 times 0 squared is 0 minus 3 is negative 3 all over 0 squared minus 9 is negative 9. And so that's going to be equal to 1/3. And so that is the point 0. That's what we plugged in for x. We got out 1/3. So that right there is going to be my y-intercept. This is my set of x-intercepts. 0, 1/3 is not plotted yet. I'll do that in a slightly different color, just so that you're seeing that we're doing slightly different things here. So right there, 0, 1/3. Okay, next we've got to look for asymptotes, right? So let's start out first by looking for our vertical asymptote. Remember, that happens when it's a number over 0. Your denominator's got to equal 0, but not the numerator. Well, the denominator will equal 0 at two places, when x equals 3 and when x equals negative 3. So I'll write out two separate equations for the vertical lines. Because when x is 3, 3 minus 3 is 0. When x is negative 3 plus 3, we get 0. So those are our vertical asymptotes. Excellent. So let's put them on the board, right? So literally just kind of dotted lines there. And again, I want to remind you, these are just rough sketches, that's all. So they don't have to be perfect. The real benefit in all of this is in doing the review that we're doing in our work, honestly. So those are our vertical asymptotes. Cool. All right, so we'll see how the function's behaving around that vertical asymptote in a little while. Now we've got to look for possible horizontal asymptotes or end behavior, or slant asymptotes. You'll have one or the other, but not both. Now a horizontal asymptote will occur, and by the way, you can look back in chapter 1 to review horizontal asymptotes if you need to, but they'll occur when the degree of the numerator and denominator are either the same or the denominator's degree is greater than the numerator's. If, this is important, if the numerator's degree is 1 more than the denominator, then we know we'll have a slant asymptote, and I'll go over an example of that down the road. That's because you'd have a degree, 1 degree greater than the denominator makes it act like we're a line. A slant asymptote either that way or that way. All right, we'll get to that down the road. Not here though. Here we've got the limit, and technically you should take the limit as x goes to both positive and negative infinity of this function. Now recall back from chapter 1, and you can always look back at it, that when I'm doing horizontal asymptotes or investigating for them, I only look at the two highest degrees, right? Because minus 3 and the minus 9 don't really factor in to what the horizontal asymptote is. Here the x squareds are going to divide out, and you're going to be left with the limit as x goes to infinity of 3, which is just 3. So we're going to have a horizontal asymptote at y equals 3. Now technically, you should always check negative infinity too. So I want to be very formal here. You're going to check negative infinity because you're checking to the left to see the horizontal asymptote exists and is the same. Well again, you'll still get 3x squared over x squared. which still is going to simplify to 3. So yeah, we've got a horizontal asymptote at y equals 3. I'll do that in black here. So y equals 3, there we have it. Now you can cross a horizontal asymptote. You cannot cross a vertical one, but it's one of those pieces of information that some people mistake, and they say, I can't cross that. Yes, you can. And that's it for our pre-calc information. Whoop, I'll box it. It's pre-calc. Now let's go into the derivative, and this is where things get a little bit gross. So what I've set up is a separate page to do our derivative work, and then we're going to take over the simplified derivative and use it over here to do our sign chart. Okay, so we'll do our y prime down here, but we're going to do our work on the next page. So we got 3x squared minus 3 over x squared minus 9, right? That was our original function. And we'll call that y or f of x. It doesn't really matter. I guess it was f of x. So we'll be formal here and call it f of x. A little bit of extra work. So we're going to do the quotient rule here. Ugh, I know, right? We got this. We got it. F prime is equal to the bottom times the derivative of the top. So the x squared minus 9 times the derivative of the numerator is 6x minus the top, 3x squared minus 3, times the derivative of the bottom, which is 2x, all over x squared minus 9 squared. Okay. Now, before we get all crazy and say, oh my gosh, that's terrible, let's just kind of write this one out, see what we end up with. So we end up with 6x cubed, just distributing the 6x, minus, well, that's pretty bad, minus 54x, minus 6x cubed. Ooh, that's nice. That's very nice. Minus a minus 3 is a plus 3 times 2x is plus 6x. Actually, this ended up getting nicer. Well, that's sweet. All right, so we're going to combine some terms. And you see why I'm doing the work on a separate page. It's pretty messy, and I advise you to do this too. Keeps things neater in terms of our grand scaled work. 6x cubed minus 6x cubed is 0. Minus 54 plus 6x is a minus 49x. And I always like to go back and check my distribution because there's so much algebra in this. I want to make sure that everything's working out correctly, not to make like a simple algebra mistake. That'd be terrible. Alrighty then, this is awesome. Okay, so now what we've got here is we can set all of this equal to 0. Like I said, I'm just going to put the conclusions on the next page, or that last page. So we want to know, remember, where the derivative is equal to 0 or does not exist. Well, a real quick look at this shows that we're going to equal 0 when the numerator is 0 and the denominator is not. That'll happen at x equals 0. That's pretty nice. So that's a critical number. Another critical number would be, well, two of them. X equals negative 3 and 3, because that's where the denominator is equal to 0. Okay, let's take those critical numbers. So I'll call them critical numbers. And let's move them on over to that previous page. All right. So we've got, I'm not even going to put the y equals there. We don't really need it. We're going to do our sign charts and just kind of stack them on top of each other. So I've got a sign chart here. And remember our critical numbers. We had negative 3, 0, and 3. And this is y prime, and it's going to tell us stuff about y. So now, one thing that I do need to translate over is what y prime was. So we've got y prime, or f of x, I suppose. Let's keep it consistent. So that'd be f prime, just to be consistent after all, right? So I've got f prime, and then I've got f. Now f prime was, I believe it was what, negative 49x over x squared minus 9 squared. So negative 49x over x squared minus 9 squared. And these problems do take a while. Think about all you're combining in them. So negative 49x, again, we already solved this out. We're going to use this for the signs of things, and you're going to like this, I think. Pick a value to the left of negative 3, negative 42 billion. Times a negative is a positive. Keep in mind, anything squared is positive, so the denominator never really factors in to the signs. It's always positive, always. So we got a negative times a negative is a positive, so f is increasing. Then from negative 3 to 0, negative 1. Negative times a negative is a positive. That's always positive, so we're still positive, still increasing. Isn't that sweet? I think so too. 0 to 3, 1. Negative times positive 1 is a negative. Always positive, so we got a negative, so now we're decreasing. And greater than 3, 82 billion. times negative 49 is negative, divided by a positive is still negative. So now keep in mind that we could not have had a relative max or min at negative 3 or 3, because those are places where we have vertical asymptotes. But we still could have changed increasing to decreasing or vice versa there. So that's why we have to check at the vertical asymptotes. The critical numbers always get checked, even if there's an undefined point. Okay, so from here then, we have a max at, and that's going to be the point 0. Let's plug in 0. What do we get? If I plug in 0, well, we already know what we get. We got that at the y-intercept, 0, 1/3. So we've got a local max at 0, 1/3 because we're changing from positive to negative. Yeah, that kind of looks like it makes sense. What's coming up next, you ask? Well, of course, we're going to need a chart for f double prime. All right, so let's go and take a look at that and see how that all fits into the grand scale of things. And you know what? I'm going to need a little bit more room there for this. All right, let's do it. And of course, these problems take a while. You're doing a lot here. So we're going to take a derivative of this thing. So f double prime of x is equal to bottom d top. So that's x squared minus 9 squared times the derivative of the top is negative 49 minus top. So minus a minus 49 is a plus. That's minus the top. D bottom. Okay, hold on here. Chain rule. 2 times x squared minus 9 times the derivative of the inside, 2x. All over the square of the bottom, which is x squared minus 9 to the 4th. Okay, let's keep rocking and rolling. Now the first thing I notice here is that we actually have a GCF that's pretty nice. We can factor out a negative 49 out of all of this and an x squared minus 9. That's in both of these terms, separated by the plus. So negative 49 times x squared minus 9, that leaves us with 1x squared minus 9 because it was squared. Hang on to your algebra hats here. Then you've got the x squared minus 9 and the 49 out of there, but it's a minus, right, because we factored out the negative. And you're going to have x squared, 4x squared. So you have minus 4x squared right there. Double check that. Again, we pulled out the 49 and the x squared minus 9 and a negative, so you're left with minus 4x squared. All right, that's all over x squared minus 9 to the 4th. Oh, dear goodness. These are going to cancel to the extent that you'll have this to the 3rd power. So we end up with negative 49 times, this is minus 3x squared minus 9. Whew. All over x squared minus 9. Getting there, peeps. Cubed. And that's going to end up equaling out to, well, we can pull out a negative 3 times a negative 49 is a positive. I think that's going to be 147 times, and then you'll be left with x squared plus 3. Wow. Okay, why is that important? Well, let's take a look at it. That's going to be important because x squared plus 3 shows that we're not going to have a point of inflection, right? So we want to go back and double check our signs here. That's extremely important because if we do end up having anything going on there, we want to be sure that, we didn't skip over a point of inflection. So I jump back over this, just make sure my signs are good, and it looks like we're in great shape, right? So I always double check over that algebra. It's worth it because it's hellacious to start this over again. Now here's the other thing to look for. Possible points of inflection happen where f double prime equals 0 or does not exist. Now, the numerator is always positive. X squared plus a number is never, ever negative. So we're not going to change signs. So that's never going to happen. But it does not exist at x equals plus or minus 3. So we're going to check those on our sign chart. Knowing that there's a vertical asymptote there, we're still going to check it. Okay. So f double prime is equal to 147 times, it was x squared plus 3, all over, and that's going to be, let's see, x squared minus, I believe it was 9 cubed. Okay, we've got another sign chart to check. Almost done, y'all. Almost done. Coming up on 15 minutes. I know it's a lengthy one, but you got this. That's why if on a test, you're hopefully only going to be given one of these. And so this would be f that we're looking at, and we're going to line them up. Negative 3, 3 to 3, so that we don't confuse anything later. And we're just going to check the signs of the second derivative. A number to the left of negative 3 is negative 40 billion. The numerator is always positive. Don't even consider it. The denominator is not always positive because it's cubed. So that's something huge and positive. Cubed is still positive. So we're concave up. So CC up. Then we'll plug in 0. The numerator is positive. 0 minus 9 is negative. Cubed is still negative, so we're concave down there. And this will make a lot of sense with our graph. Very satisfying when we get to our final answer. And then greater than 3 is 80. Positive. Big minus 9, still positive. Cubed is positive. So now we're concave up. All right, we're ready to rock and roll. There are no points of inflection, again, because we had vertical asymptotes and no points at -3 and 3. So we're just going to use everything piece by piece. Let's graph it. I'm psyched. We put in so much work. So from -infinity to -3, we are increasing and concave up. Okay, so how would that look? Well, let's pick a point to the left here just to know what side of the horizontal asymptote we're on. So other points, and I'll plug in like x equals -4. So I'll do f of -4, and that's going to be equal to 16 times 3 is 48, minus 3 is 45, and then 16 minus 9 is 7. Not a nice number, but whatever. So that's -4, 45/7. So -4 at 45/7 is just shy of, let's see, 7. So that's going to be somewhere around here-ish. But that gives us all we need because we're increasing and concave up. So there's your horizontal asymptote, increasing and concave up the whole time. Boom, one branch done. So now from -3 to 0 is where we stop at. We are going to be concave down and increasing. Ah, I know where this is going. All right, here's your vertical asymptote. So there's increasing and concave down. Beautiful. We reach our maximum here, which we knew at 0, 1/3. The next part, we're decreasing and concave down. Well, that looks like this. Ah, isn't that beautiful? That's a beautiful curve. And now, again, we're going to pick the point, maybe x equals 4. I typically pick values near the vertical asymptote just to see, again, what side of the horizontal asymptote we're on. F of 4, we plug it in, we're actually going to get the same answer. 48 minus 3 is 45. 4 squared is 16 minus 9 is 7. So we get 4 45/7. So 4 45/7 again, just a little bit shy of 7. So here we're going to be concave up and decreasing. So this would be concave up and decreasing the entire time. Isn't that satisfying? That's awesome. So yeah, it's a lengthy problem, but look at all the work we did. Yes, it is a lengthy problem. Is it difficult? Not if you take your time and break it into pieces and have the confidence that you can do each part. So break the video down into pieces if you need to. I will see you in the next problem. Psyched for it.